Performance. Objectives. After completing this section, you will get familiar with general information, use of performance tables and diagrams, takeoff distance, climb performance, time, fuel, and distance to climb, cruise performance, landing distance, go-around climb performance, and other performance-related data. General information. This lesson of the DA40NG contains multiple tables for performance data, according to the aircraft flight manual. As an example, the takeoff distance performance table for the normal procedure is presented in this slide. In order to view the complete data in the table, throughout this lesson, for different configurations, use the slider on the right, or scroll through the table. The performance tables and diagrams presented in the AFM have multiple roles. They can be used to present the expected performance of the airplane. They also allow comprehensive and sufficiently accurate flight planning based on the values obtained during the test flights. Airplane performance tables are based on the data gathered during the flight trials, obtained by aircraft and power plant in good conditions. After that, the gathered data is corrected to the conditions of the international standard atmosphere. The presented performance can be achieved if the procedures outlined in the manual are followed. The airplane is well maintained and well operated, and the crew is sufficiently trained. If the absence of wheel fairings causes any degradation of flight performance, the appropriate data will be given as a percentage. Use of performance tables and diagrams. The performance data is presented in the form of tables and diagrams to illustrate the influence of many different variables. The data in the performance tables provide sufficiently detailed information that allows conservative values to be selected and used to determine adequate performance data for the planned flight. Note: while using the tables, it is advised to use the linear interpolation between the neighboring values that are provided for temperatures, altitudes, and weights. For weights below 1,100 kilograms, use the data for the lowest weight. For outside air temperatures, lower than provided in the tables, one should use the lowest temperature shown. Extreme caution must be used in case of operating at outside air temperatures higher than the data provided in the tables, areas that are indicated with a diagonal line. The airspeed calibration can be done by using this table. Based on the indicated airspeed, the pilot can instantly read the calibrated airspeed at current flap settings. The indicated airspeed is the reading shown on the airspeed indicator. The calibrated airspeed is the indicated airspeed, corrected for installation error. The engine performance table shows the values of load setting on the engine and the fuel consumption. The pilot can estimate the fuel consumption instantly during the flight by referring to this table. For example, the engine with power set to 60% is estimated to consume 5.1 US gallons per hour. Note: the fuel calculations on the fuel calculation portion of the G1000NXI multifunction display do not use the airplane's fuel quantity indicators. The values shown are numbers, which are calculated from the last fuel quantity update, done by the pilot, and actual fuel flow data. Therefore, the endurance and range data is for information only, and must not be used for flight planning. The graph presented is used to convert the pressure altitude to density altitude. At a given temperature, the pressure altitude is the altitude indicated when the altimeter is set to 29.92 inches of mercury. Density altitude is defined as the pressure altitude, corrected for non-standard temperature variations. For example, for a reading of 900 feet on altimeter at an ambient temperature of 21 degrees Celsius, the density altitude read-off is 1,800 feet. This means that from the performance point of view, the airplane is at 1,800 feet. The graph presented is used to indicate a deviation from international standard atmosphere conditions, based on the outside air temperatures at specific altitudes. For example, if the airplane is at 8,000 feet, and the outside air temperature is 19 degrees Celsius, the resulting deviation from international standard atmosphere is plus 20 degrees Celsius. The stalling speeds for various banking angles and flaps configurations can be read from these tables. The tables are separated for the different mass values of the airplane. The indicated airspeeds are in knots. Flaps extension and the increase of the bank angle increase the stalling speed. Click on the button to view the stalling speed data for different mass values. Note: the indicated airspeed may not be accurate at stall airspeeds, most forward CG position, and with the airplane power off. The wind component diagram is used to determine the headwind component, tailwind component, or crosswind component. To get these results, the pilot should identify the flight direction, wind direction, and speed. The maximum demonstrated crosswind component for this airplane is 25 knots. As an example, for the flight direction, 360 degrees, and wind, 30 knots at 32 degrees, the resulting crosswind component is 16 knots. Takeoff distance. The takeoff distance tables for airplanes with different weights are present in the airplane flight manual. As an example, the takeoff distance table for weight 1,310 kilograms is shown here. The pilot can estimate the ground roll distance and the takeoff distance over a 15 meters obstacle by referring to this table. Typically, the pilot needs pressure altitude, outside air temperature, and takeoff mass to get the value of distance available for the takeoff. Click on the button to view the takeoff distance table for the normal procedure for different weight class values. The performance-related values from the tables are calculated with the following conditions. The power lever set to 92%, or a maximum of 2,100 revolutions per minute. Flaps in the takeoff position. Airspeed at nose-wheel liftoff, VR. Airspeed for the initial climb, V50. And runway condition being dry, paved, and level. Additionally, the following factors should be considered, as they affect the computed takeoff distance. Warning: for a safe takeoff, the available runway length must be at least equal to the takeoff distance over a 50 feet obstacle. Warning: poor maintenance condition of the airplane Deviation from the given procedures as well as unfavorable outside conditions, high temperature, rain, unfavorable wind conditions, including crosswind, will increase the takeoff distance. Caution. The factors and the corrections mentioned in the former slides are typical values. On the wet ground, or wet soft grass-covered runways, the takeoff roll may become significantly longer than stated. In any case, the pilot must allow for the condition of the runway to ensure a safe takeoff. Caution. The corrections for runway slope should be used with caution, since published runway slope data is usually the net slope from one end of the runway to the other. Runways may have positions at their length, at greater or lesser slopes than published slope, lengthening, or shortening the takeoff roll, estimated with these tables. Note: the effective 50% of the headwind component and 150% of the tailwind component is already incorporated in the head and tailwind factors. Climb performance. The takeoff climb performance tables for airplanes with different weights are present in the airplane flight manual. By knowing the outside air temperature, flight mass, and pressure altitude, the rate of climb can be determined. The performance-related values from the tables are calculated with the following conditions. Power lever set to 92%, or a maximum of 2,100 revolutions per minute. Flaps in the takeoff position. And airspeed of 72 knots. Indicated airspeed must be fulfilled. Note: the gradient of climb can be calculated using the following formulae. Note: for operation without wheel fairings in takeoff climb, a climb rate decreased by 20 feet per minute must be expected. Note: if mandatory design change advisory 40662 is installed, the rate of climb at maximum takeoff mass, with a power setting of 100% at mean sea level, and international standard atmosphere conditions is 714 feet per minute. The cruise climb performance tables for airplanes with different weights are present in the airplane flight manual. To determine the rate of climb for a cruise, the following information are required. Flight mass, pressure altitude, and outside air temperature. The performance-related values from the tables are calculated with the following conditions. Power lever set to 92%, or a maximum of 2,100 revolutions per minute. Flaps in the up position. And airspeed of 88 knots. Indicated airspeed. Note: the cruise climb table shows the rate of climb. The gradient of climb cannot be easily determined with a graph, but it can be calculated using the following formulae. Note: for operation without wheel fairings in cruise climb, a climb rate decreased by 40 feet per minute must be expected. Time, fuel, and distance to climb. To calculate the time, fuel, and distance to climb, the table shown on this slide is used. In order to do that, the following parameters are required. Initial climb weight of the airplane, airfield pressure altitude, cruise altitude, outside air temperature at takeoff, and outside air temperature at cruise altitude. The performance-related values from the tables are calculated with the following conditions. Power lever set to 92%, or at maximum 2,100 revolutions per minute. Flaps in up position. And airspeed of 88 knots. Indicated airspeed. Note: distances shown in the time, fuel, and distance to climb table are based on zero wind. Fuel for start, taxi, and takeoff are not included. Add 5% to the time and fuel, and 10% to the distance, for each 10 degrees Celsius increase in outside air temperature. As an example, let us calculate the unknown time, fuel, and distance to climb from the airfield to the cruise altitude. Given the outside air temperature at the takeoff, 11 degrees Celsius, airfield pressure altitude, 2,000 feet, initial climb weight, 1,310 kilograms, outside air temperature at cruise, minus 17 degrees Celsius, and a cruise altitude, 16,000 feet. To see the solution, proceed to the next slide. Read the time, fuel, and distance to climb at the airfield altitude. Mark them as the first set of data. Then, read the time, fuel, and distance to climb at the cruise altitude. Mark them as the second set of data. To calculate the time, fuel, and distance to climb from the airfield to the cruise altitude, subtract the first set of data from the second set. The final results are as follows. Time to cruise altitude, 23 minutes. Fuel to cruise altitude, 3.3 US gallons. And distance to cruise altitude, 38 nautical miles. Cruise performance. To determine the cruise performance of the DA40NG, the table shown on this slide is used. Based on the outside air temperature, cruise pressure altitude, and power setting, the fuel consumption, and true airspeed can be determined. The performance-related values from the tables are calculated for the following conditions. Flaps in the up position, landing gear retracted, and weight of the airplane equal to 1,310 kilograms. Note: for operation without wheel fairings, a performance reduction of 4% true airspeed at all power settings must be expected. Landing distance. The landing distance is influenced by the following factors: the weight of the airplane, the pressure altitude, and the outside air temperature. The table above can be used to determine the landing distance, with flaps in the landing position, for one particular weight class of the airplane. Click on the button to view the landing distance table, with flaps in the landing position, for different weight class values. The table above can be used to determine the landing distance with flaps in the abnormal position, that is flaps in the takeoff or up positions, for a particular weight of the airplane. The values in the table are landing distance over a 15 meters obstacle and the ground roll distance. They are influenced by the outside air temperature and the pressure altitude. Click on the button to view the landing distance table, with flaps in the abnormal position, for different weight class values. The performance-related values from the tables are calculated for the following conditions. Power lever in the idle position. Flaps in landing, takeoff, or up position. Runway condition being dry, paved, and level. And approach speed, V reference. Additionally, the following factors should be considered, as they affect the computed landing distance. Warning: for a safe landing, the available runway length must be at least equal to the landing distance over a 50 feet obstacle. Warning: poor maintenance condition of the airplane, deviation from the given procedures, uneven runway, as well as unfavorable external factors, will increase the landing distance. Caution: The factors in the corrections mentioned earlier are typical values. On wet ground, or wet soft grass-covered runways, the landing distance may become significantly longer than stated above. In any case, the pilot must allow for the condition of the runway to ensure a safe landing. The corrections for runway slope should be used with caution, since published runway slope data is usually the net slope from one end of the runway to the other. Runways may have positions at their length at greater or lesser slopes than published slope, lengthening or shortening the landing roll, estimated with these tables. Note: the effective 50% of the headwind component and 150% of the tailwind component is already incorporated in the headwind and tailwind factors. Note: higher approach speeds result in a significantly longer landing distance during a flare. Go-around climb performance. The go-around climb performance table provides the rate of climb of the airplane. The rate of climb is influenced by the weight of the airplane, pressure, altitude, and outside air temperature. The performance-related values from the tables are calculated with the following conditions: power lever set to maximum, flaps in landing position, and airspeed V reference. Note: the tables for the climb performance show the rate of climb of the airplane. The gradient and angle of climb can be calculated using the following formula. Note: the angles of climb at mean sea level and indicated airspeed conditions are 3.0 degrees for maximum takeoff mass, or maximum landing mass of 1,280 kilograms, and 3.6 degrees for maximum landing mass of 1,216 kilograms. If mandatory design change advisory 40662 is carried out, the angle of climb is 2.9 degrees for maximum takeoff mass of 1,310 kilograms. Other performance-related data. To achieve the best glide ratio, the aircraft should fly with the flaps retracted and at an airspeed of 88 knots indicated airspeed. The DA-40NG airplane, gliding in still air with a windmilling propeller, can achieve a glide ratio of 1 to 9.7. It means that it can glide for a maximum horizontal distance of 1.59 nautical miles per 1,000 feet of altitude loss. Caution: the propeller will keep windmilling under all expected conditions. Do not attempt to stop the propeller intentionally. Note: in case of stationary propeller, the given numbers are conservative. For operation without wheel fairings, the glide ratio is reduced to 9.4. That is, for every 1,000 feet of altitude loss, the maximum horizontal distance traveled in still air is 1.54 nautical miles. According to ICAO Annex 16, Chapter 10, and CS 36 Subpart C, the approved noise level for DA-40NG, weighing 1,280 kilograms, is 74.5 decibels. For the same airplane with an exhaust pipe and muffler installed, the noise limit is decreased to 71.5 decibels. For the DA-40NG weighing 1,310 kilograms, the approved noise level is 71.4 decibels. Summary. With this section, you got familiar with general information, use of performance tables and diagrams, takeoff distance, climb performance, time, fuel, and distance to climb, cruise performance, landing distance, go-around climb performance, and other performance-related data.